Hello. In this video, I'm going to explain problem 25 from the 2015 F equals MA contest. We have two identical carts A and B, each with mass M, and they're connected via a spring with spring constant K. And there are two additional springs identical to the first, connected to two fixed points on the wall. And we are told that the carts can given the right initial conditions, the two carts will oscillate in phase. And given the other initial conditions, the carts will oscillate out of phase. And we're asked to find the ratio, omega 2, where omega 2 is the ratio of out of phase oscillations, and omega 1, where they are in phase. So what do these two conditions look like? So when they're in phase, we have x1 of t equals x2 of t. And so these carts, I'll just draw them as boxes, will basically, so let's say these are the equilibrium points, and I realize I didn't draw the carts very well. They'll basically oscillate perfectly like this. And when they're out of phase, we get x2 of t is negative x1 of t. And so we'll get something like if the equilibrium points are here, then you can see that this is x1, like this, going off to the left, and if x1 is going off to the left, then x2 will go off to the right. So it looks something like this. So what that means, so now we need to ask, how do the two omegas relate? And the key to answering that is to ask, how do the strength of the restoring forces compare? And so what we can do, so let's look at these two masses and what happens. Well, notice that this spring right here, let's look at the in-phase case. We have, let's say they both move off by a certain amount, x2 or x1, which equals x2. Then, since they both move off to the left the same amount, or right the same amount, then this spring is actually not stretched at all. And then this spring right here is stretched, or compressed, excuse me. So this is not stretched or compressed. Then this guy is compressed in this diagram, but of course it could be stretched if we move the cart the other way, by the quantity x1, and this guy is stretched, since the cart goes off to the left, so it's going farther away from the right wall, by x2, which equals x1. And so thus, our restoring forces are going to be, let's draw them in red. Here we get kx1 from this spring right here, from the leftmost spring, and then on this block we're going to have kx1 to the right from the rightmost spring, since it's getting stretched, and so it'll want to shorten back to its natural length. And thus we see that, remember that on any one object, the omega squared is equal to the ratio of the spring constant to the mass, where the spring constant, or the effective spring constant, is basically the proportionality constant between the total restoring force and the total displacement. And in this case, the effective spring constant is just the spring constant of one of the springs, and the effective mass is just one of the masses, because we can look at each individual mass, and each one has a force kx1 on it, where x1 is the displacement. But now let's look at the second setup where they are out of phase. So what happens here? So actually, let's continue this black for now. So now notice that since these two carts move off in opposite directions, this one right here, the middle spring is actually, in this case, stretched by a quantity 2x1. And so it's actually going to apply double. Before it was not applying any restoring force at all, but now it's actually going to apply double the restoring force. We're going to get 2kx1 in this direction and 2kx1 in that direction. And we're just going to write everything in terms of x1 for convenience. And then this spring right here is compressed by x1 because the left cart moves x1 toward the left wall. And the cart on the right is also compressed by x1. And again, if we move the carts in the opposite directions, then they would be stretched, but it'll still apply a restoring force, as you can see fairly easily. And so this guy right here will apply a force kx1, and then this guy will also apply a force in this direction, kx1. And so notice that the total restoring force on either of the masses is now 3kx1. So you get 1kx1 from one of the springs on the side and 2kx1 from the spring in the middle. And thus we get that the total force is 3kx. So the effective spring constant is now 3k, and the mass is m. So now we have omega 1 squared is k over m, omega 2 squared is 3k over m, and thus we get that omega 2 squared over omega 1 squared is equal to 3. So omega 2 over omega 1 is equal to the square root of 3. So this is our answer. One interesting thing is that these two situations where the two carts oscillate exactly in phase or exactly out of phase are what are called the normal modes of this system. And basically, even if we had some other initial conditions, what turns out to be the case is that the combination can always be expressed as what's called a linear combination of the two normal modes. So we would basically be able to write each cart's position as a sum of two oscillations. And those oscillations would be exactly the forms of these normal modes, but with some coefficients attached. And basically, normal modes are exactly those situations where all of the objects that are basically coupled by these sort of forces that interact between them, where all the objects basically oscillate in a manner where they all have basically the same oscillation, just up to constant factors. And so that's just something interesting that you will learn perhaps in some physics course in college, or maybe if you study more for the semi-final exam or something like that, you'll learn a little bit more about this. All right, but that's all there is to the problem. Thank you for watching, and I hope that was helpful.